Okay, example 5.9 is inclined venturimeter. So you see, a venturimeter, it could be horizontal or vertical sometimes. Sometimes it could be inverted and sometimes it is inclined. Or sometimes you may have differential manometer. So the following data relate to an inclined venturimeter. This is inclined venturimeter. So diameter of the pipeline is given 400 millimeter. So this is the pipeline. Here the same dimension, but here the throat you have. So the throat diameter is given. Inclination of the pipeline with horizontal 30 degree. So this is inclined with 30 degree. The distance between the mouth and the throat of the meter is 600 millimeter. So the distance between the throat and the inlet of the pipe, 600 millimeter. Specific gravity of oil flowing through the pipeline is 0.7, and specific gravity of heavy liquid, which is this one, mercury, is given 13.6. Reading of differential manometer, so displacement you are given is 50 millimeter. Coefficient of the venturimeter is 0.99. So determine the rate of flow of the pipeline. So what will be the flow rate passing through this? So I think everything is given. So what will happen? Now let us see. So as usual, you have to just make consistent of the units of measurement. D1 is this one, 0.4 meter. Area pi over 4 D1 square, this one. Throat diameter, then area of the throat, this volume. So reading of the differential manometer in the U-tube, you have 50 millimeter, convert into meter, 0.05 meter. So difference in pressure head is given by the previous equation. Pressure difference P1 minus P2 over gamma equal to X times Sm over S minus 1. Then equal to, after substitution, you get 0.92 meter of oil. So this is a pressure head difference between the two parts. So now you can apply Bernoulli's equation at section 1 and section 2. Bernoulli's equation at section 1 and section 2. This is section 1. Then section 2 is this one. So what will happen? So don't forget to consider the inclination angle. Now P1 over specific weight plus potential head at section 1, velocity head at section 1 equal to pressure, potential, the velocity head. So rearrange this equation. So it may be noted that differential gauge reading will include in itself the difference of pressure head and the difference of datum head, which means just if you rearrange this equation, so this means pressure head difference between inlet and outlet, or between inlet and throat. So H, you can substitute here H, then this is velocity difference, V1 square over 2G minus V2 square over 2G. Then again, you can apply continuity equation at section 1 and section 2. We get A1 V1 equal to A2 V2. So rearranging this equation, you can find the expression for V1 in terms of A2 over A1. Then V2 is unknown, so V2 over 4. So V1 is V2 over 4. So substitute the value of V1 and H in the equation 2, in the above equation. Then simply H already calculated 0.92. Then V2 square over 15 times 2G. Already we have found this V2 over 4. If you square it, 15, V2 square over 2G. So from this you can find total velocity in throat, 4.38 meters per second. So once you have velocity, then you can apply according to continuity equation, you can apply flow rate, A2, V2, then this is the flow rate passing through the inclined venturimeter. So once you have discharge, then other parameters can be computed like this. So I hope it is clear that you can find every calculation using this inclined venturimeter. So if you need, for example, just pressure difference between Z1 and Z2, you may have distance just sin 30. Sin 30 is opposite over hypotenuse, so you have 0.6, then please substitute that one. Then finally, you can find the equation. If you are asked what will be the pressure head difference, or what will be Z in Z1 and Z2. Okay, so the other as exercise, this is inverted and inclined venturimeter. Please, as exercise, try this problem. What will be the flow rate of water passing through this inclined venturimeter. This is as exercise. Okay, example 5.10 is Pitot tube. So if you have flow here, you can insert any pipe, then you have stagnation pressure. So P naught over gamma at this point, stagnation pressure, you can find. Static pressure, this is piezometer. You can substitute flow is going through this, then pressure at A over gamma will be at this point, you can find total pressure head. So Pitot tube, another instrument for measuring or application of the Bernoulli equation for measuring the flow rate. So a Pitot tube having coefficient of discharge 0.898 is used to measure the velocity of water at the center of the pipe, the velocity of water at the center of the pipe. You see, at the center of the pipe, you can measure using Pitot tube. And also calculate the velocity when the stagnation pressure and the static pressure are 6 meter and 5 meter. So stagnation pressure and static pressure given, so you simply substitute. So applying the Bernoulli equation between A and O, point A is this one, point O is this one. So static pressure will be developed due to this point, flow due to this piezometer, and stagnation pressure is this one. So PA over gamma, VA square over 2G plus ZA equal to P naught over gamma, V naught square over 2G plus Z naught. So I hope elevation the same. ZA is equal to Z naught, and V naught initially it is at rest 0. Then finally it will go like this, then you can substitute. So VA square over 2G, P naught over gamma minus PA over gamma. So this is pressure head already given, static pressure and stagnation pressure head already given, 6 minus 5 will be 1. So rearrange this equation. To account for turbulence, we will introduce coefficient of discharge. So CD square root of 2GH. So 2G here, you have H, this one, 2GH. So 1 meter is just velocity head at this point A. Then you can find the velocity, which is calculate the velocity. The velocity at the center of the pipe will be 3.977 meter per second. I think this is very simple. And the other exercise is orifice flow. So if you have a reservoir with 3.4 meter height, then you may have an orifice located at 1.8 meter from the bottom of the tank. 1.8 meter from the bottom of the tank. Calculate the speed of water passing out from the orifice and calculate the distance at which the water leak hits the ground. Take coefficient of velocity due to this orifice. You have 0.98. Actually, orifice, you have different shapes. You may have, for example, sharp, edged orifice, rounded orifice, and sometimes rectangular, and sometimes border orifice, etc. So different coefficient of discharge may be given. So for this specific problem, let us take coefficient of velocity due to the shape of the orifice here, 0.98. So let us find, according to Orifice principle, velocity passing out through this one will be square root of 2G H1. So the head above this point, which is 1.6. 3.4 minus 1.8 will be 1.6. So velocity passing out through this one. So we can just apply from this point onwards, you can apply projectile motion. I hope you have enough background from physics, projectile motion. So once you found this velocity 5.49 meter per second, so you have here two direction velocity, v initial x and v initial y. So for projectile motion, we have equation of vertical position, which is y. Y is just total height, this one. So y is v initial y, plus half gt square, because it is dropping to this direction. Then x distance will be calculated. So substitute. Already you have 1.8 from the bottom is given, this orifice. So substitute 1.8, then initial velocity to y direction is 0. Initial velocity x you have, which is 5.49. So after substitution, you can find time to hit the ground due to this height, 0.606 seconds. So this means that the water will hit the ground in 0.6 seconds. At what distance? Again, you apply projectile distance equation of motion, horizontal, x, because distance is given by velocity times time. So the initial x is constant, then the initial x times time will be 3.326 meters. So it will have 3.326 meter horizontal distance. So as exercise, please try this one. You have tank of 1.8 meter height standing on the ground, kept full of water. So there is an orifice in vertical side at a depth h below water surface. Find the value of h in order that the jet of water strikes the ground surface at maximum distance from the tank. So I think what will be this distance? So please apply calculus and maximization and derivation. Then you can find h 0.9 meter. This is maximum value of h. What maximum value of? Find the value of h so that maximum horizontal distance you can apply. So please use calculus. Okay, so this is also another exercise, free liquid jet. If you have free liquid jet at this point, projectile motion, trajectory motion will be found. So you will have range. So you have a velocity 4.5 meter per second at an angle of what? 6 degrees above the horizontal. So determine the equation of trajectory, maximum height attained by the jet, which is h maximum, then it will drop. So v naught cos alpha, v naught sin alpha. So you have the y direction, x direction, you can apply. So what will be the range? This one. So equation of trajectory, maximum height attained by the jet, and horizontal range by the jet, and maximum range horizontal jet by the jet is this one, x, and then maximum range r. So y will be 0 at this point. So your answer should be these values. So please try this as exercise for you. Then if you have any question, you are welcome. And the other example is weir and notch. You have triangular notch. Then for measuring the discharge, we can use this triangular V notch with a apex angle of 70 degrees. A discharge of 4.25 meter cube per second. Find the head of water over the notch. Over this notch, what will be the head, which is this one? What will be the head? So coefficient of discharge is 0.62. So you have this equation for V notch, triangular notch. You have this equation, CD 8 over 15 square root of 2g times tan theta times h over h to the power of 5 over 2. So you simply substitute, then h will be 0.28 meter. So the head of water should be 0.28 meter. To get what? 4.25 meter cube per second. So as exercise for rectangular notch, please try this one. You have this equation for rectangular notch. So notch, you may have rectangular, trapezoidal, and also triangular, etc. You can have different shapes of notch to measure the flow rate. So I think this will be part 2 impulse momentum application. So in this session, we will see force exerted in pipe bend, impact of jet on flat, inclined and curved surface, water jet striking a moving car. So as part 2, I will continue. But before that, please read the handout on fluid dynamics so that every issue will be simple. So if you have any question, please you can ask using this platform. So thank you very much. Okay. Okay, so this is all about today's tutorial. Hopefully you liked the video and thanks for watching.